In mathematics, a real number is a value that represents a quantity along a continuous line. The adjective real in this context was introduced in the 17th century by Descartes, who distinguished between real and imaginary roots of polynomials. The real numbers include all the rational numbers, such as the integer -5 and the fraction 4/3, all the irrational numbers, such as square root 2, and all transcendental numbers, such as pi. Real numbers can be thought of as points on an infinitely long line called the number line or real line, where the points corresponding to integers are equally spaced. Any real number can be determined by a possibly infinite decimal representation, such as that of 8.632, where each consecutive digit is measured in units 1/10 the size of the previous one. The real line can be thought of as a part of the complex plane, and complex numbers include real numbers. These descriptions of the real numbers are not sufficiently rigorous by the modern standards of pure mathematics. The discovery of a suitably rigorous definition of the real numbers, indeed, the realization that a better definition was needed, was one of the most important developments of 19th century mathematics. The currently standard axiomatic definition is that real numbers form the unique, complete, totally ordered field, up to an isomorphism, whereas popular constructive definitions of real numbers include declaring them as equivalence classes of Cauchy sequences of rational numbers, Dedekind cuts, or certain infinite decimal representations, together with precise interpretations for the arithmetic operations and the order relation. These definitions are equivalent in the realm of classical mathematics. The rails are uncountable, that is, while both the set of all natural numbers and the set of all real numbers are infinite sets, there can be no one-to-one function from the real numbers to the natural numbers. The cardinality of the set of all real numbers is strictly greater than the cardinality of the set of all natural numbers. The statement that there is no subset of the rails with cardinality strictly greater than and strictly smaller than is known as the continuum hypothesis. It is known to be neither provable nor refutable using the axioms of Zermelo-Fraenkel set theory, the standard foundation of modern mathematics, in the sense that some models of ZFC satisfy CH, while others violate it. History. Simple fractions have been used by the Egyptians around 1000 BC. The Vedic Solva Sutras, in 600 BC, include what may be the first use of irrational numbers. The concept of irrationality was implicitly accepted by early Indian mathematicians since Manavar, who were aware that the square roots of certain numbers such as 2 and 61 could not be exactly determined. Around 500 BC, the Greek mathematicians led by Pythagoras realized the need for irrational numbers, in particular the irrationality of the square root of 2. The Middle Ages brought the acceptance of zero, negative, integral, and fractional numbers, first by Indian and Chinese mathematicians, and then by Arabic mathematicians, who were also the first to treat irrational numbers as algebraic objects, which was made possible by the development of algebra. Arabic mathematicians merged the concepts of number and magnitude into a more general idea of real numbers. The Egyptian mathematician Abu Kamil Shuja ibn Aslam was the first to accept irrational numbers as solutions to quadratic equations or as coefficients in an equation, often in the form of square roots, cube roots and fourth roots. In the 16th century, Simon Stevan created the basis for modern decimal notation, and insisted that there is no difference between rational and irrational numbers in this regard. In the 17th century, Descartes introduced the term real to describe roots of a polynomial, distinguishing them from imaginary ones. In the 18th and 19th centuries, there was much work on irrational and transcendental numbers. Johann Heinrich Lambert gave the first flawed proof that pi cannot be rational. Adrien Marie Legendre completed the proof, and showed that pi is not the square root of a rational number. Paolo Ruffini and Niels Henrik Abel both constructed proofs of the Abel-Ruffini theorem, that the general quintic or higher equations cannot be solved by a general formula involving only arithmetical operations and roots. Évariste Galois developed techniques for determining whether a given equation could be solved by radicals, which gave rise to the field of Galois theory. Joseph Liouville showed that neither e nor e2 can be a root of an integer quadratic equation, and then established the existence of transcendental numbers. Georg Cantor extended and greatly simplified this proof. Charles Hermite first proved that E is transcendental, and Ferdinand von Lindemann showed that pi is transcendental. Lindemann's proof was much simplified by Weierstrass, still further by David Hilbert, and has finally been made elementary by Adolf Hurwitz and Paul Gordon. The development of calculus in the 18th century used the entire set of real numbers without having defined them cleanly. The first rigorous definition was given by Georg Cantor in 1871. In 1874, he showed that the set of all real numbers is uncountably infinite, but the set of all algebraic numbers is countably infinite. Contrary to widely held beliefs, his first method was not his famous diagonal argument, which he published in 1891. See Cantor's first uncountability proof. Definition. The real number system can be defined axiomatically up to an isomorphism, which is described hereafter. There are also many ways to construct the real number system, for example, starting from natural numbers, then defining rational numbers algebraically, and finally defining real numbers as equivalence classes of their Cauchy sequences or as Dedekind cuts, which are certain subsets of rational numbers. Another possibility is to start from some rigorous axiomatization of Euclidean geometry and then define the real number system geometrically. From the structuralist point of view, all these constructions are on equal footing. Axiomatic approach. Let denote the set of all real numbers. Then, the set is a field, meaning that addition and multiplication are defined and have the usual properties. The field is ordered, meaning that there is a total order such that, for all real numbers x, y and z, if xy then x plus zy plus z, if x0 and y0 then xy0. The order is Dedekind complete, that is, every non-empty subset S of with an upper bound in has a least upper bound in. The last property is what differentiates the reals from the rationals. For example, the set of rationals with square less than 2 has a rational upper bound but no rational least upper bound, because the square root of 2 is not rational. The real numbers are uniquely specified by the above properties. More precisely, given any two Dedekind complete ordered fields 1 and 2, there exists a unique field isomorphism from 1 to 2, allowing us to think of them as essentially the same mathematical object. For another axiomatization of, see Cauchy's axiomatization of the reals. Construction from the rational numbers. The real numbers can be constructed as a completion of the rational numbers in such a way that a sequence, defined by a decimal or binary expansion like converges to a unique real number, in this case pi. For details and other constructions of real numbers, see construction of the real numbers. Properties. Basic properties. A real number may be either rational or irrational, either algebraic or transcendental, and either positive, negative, or zero. Real numbers are used to measure continuous quantities. They may be expressed by decimal representations that have an infinite sequence of digits to the right of the decimal point. These are often represented in the same form as 324.8231222147. The ellipsis indicates that there would still be more digits to come. More formally, real numbers have the two basic properties of being an ordered field, and having the least upper bound property. The first says that real numbers comprise a field, with addition and multiplication as well as division by non-zero numbers. which can be totally ordered on a number line in a way compatible with addition and multiplication. The second says that, if a non-empty set of real numbers has an upper bound, then it has a real least upper bound. The second condition distinguishes the real numbers from the rational numbers. For example, the set of rational numbers whose square is less than 2 is a set with an upper bound but no least upper bound. Hence the rational numbers do not satisfy the least upper bound property. Completeness. A main reason for using real numbers is that the rails contain all limits. More precisely, every sequence of real numbers having the property that consecutive terms of the sequence become arbitrarily close to each other necessarily has the property that after some term in the sequence the remaining terms are arbitrarily close to some specific real number. In mathematical terminology, this means that the rails are complete. This is formally defined in the following way. A sequence of real numbers is called a Cauchy sequence if for any epsilon greater than 0 there exists an integer n such that the distance xn minus xm is less than epsilon, for all n and m that are both greater than n. In other words, a sequence is a Cauchy sequence if its elements xn eventually come and remain arbitrarily close to each other. A sequence converges to the limit x if for any epsilon greater than 0 there exists an integer n such that the distance xn minus x is less than epsilon provided that n is greater than n. In other words, a sequence has limit x if its elements eventually come and remain arbitrarily close to x. Notice that every convergent sequence is a Cauchy sequence. The converse is also true. Every Cauchy sequence of real numbers is convergent to a real number. That is, the rails are complete. Note that the rationals are not complete. For example, the sequence, where each term adds a digit of the decimal expansion of the positive square root of 2, is Cauchy but it does not converge to a rational number. The existence of limits of Cauchy sequences is what makes calculus work and is of great practical use. The standard numerical test to determine if a sequence has a limit is to test if it is a Cauchy sequence, as the limit is typically not known in advance. For example, the standard series of the exponential function converges to a real number because for every x the sums can be made arbitrarily small by choosing n sufficiently large. This proves that the sequence is Cauchy, so we know that the sequence converges even if the limit is not known in advance. The complete ordered field, the real numbers are often described as the complete ordered field, a phrase that can be interpreted in several ways. First, an order can be lattice complete. It is easy to see that no ordered field can be lattice complete, because it can have no largest element, so this is not the sense that is meant. Additionally, an order can be Dedekind complete, as defined in the section Axioms. The uniqueness result at the end of that section justifies using the word the in the phrase complete ordered field, when this is the sense of complete that is meant. This sense of completeness is most closely related to the construction of the rails from Dedekind cuts, since that construction starts from an ordered field and then forms the Dedekind completion of it in a standard way. These two notions of completeness ignore the field structure. However, an ordered group defines a uniform structure, and uniform structures have a notion of completeness. The description in the previous section completeness is a special case. It is not true that R is the only uniformly complete ordered field, but it is the only uniformly complete Archimedean field, and indeed one often hears the phrase complete Archimedean field instead of complete ordered field. Every uniformly complete Archimedean field must also be Dedekind complete, justifying using the in the phrase the complete Archimedean field. This sense of completeness is most closely related to the construction of the rails from Cauchy sequences, since it starts with an Archimedean field and forms the uniform completion of it in a standard way. But the original use of the phrase complete Archimedean field was by David Hilbert, who meant still something else by it. He meant that the real numbers form the largest Archimedean field in the sense that every other Archimedean field is a subfield of R. Thus R is complete, in the sense that nothing further can be added to it without making it no longer an Archimedean field. This sense of completeness is most closely related to the construction of the rails from surreal numbers, since that construction starts with a proper class that contains every ordered field and then selects from it the largest Archimedean subfield. Advanced properties: the rails are uncountable, that is, there are strictly more real numbers than natural numbers, even though both sets are infinite. In fact, the cardinality of the rails equals that of the set of subsets of the natural numbers. And Cantor's diagonal argument states that the latter set's cardinality is strictly greater than the cardinality of n. Since the set of algebraic numbers is countable, almost all real numbers are transcendental. The continuum hypothesis can neither be proved nor be disproved. It is independent from the axioms of set theory. As a topological space, the real numbers are separable. This is because the set of rationals, which is countable, is dense in the real numbers. The irrational numbers are also dense in the real numbers. However, they are uncountable and have the same cardinality as the rails. The real numbers form a metric space. The distance between x and y is defined as the absolute value, x minus y, by virtue of being a totally ordered set. They also carry an order topology. The topology arising from the metric and the one arising from the order are identical, but yield different presentations for the topology. In the order topology as ordered intervals, in the metric topology as epsilon balls. The Dedekind-Cutts construction uses the order topology presentation, while the Cauchy sequences construction uses the metric topology presentation. The rails are a contractible, separable and complete metric space of Hausdorff dimension 1. The real numbers are locally compact but not compact. There are various properties that uniquely specify them. For instance, all unbounded, connected, and separable order topologies are necessarily homeomorphic to the rails. Every non-negative real number has a square root in R, although no negative number does. This shows that the order on R is determined by its algebraic structure. Also, every polynomial of odd degree admits at least one real root. These two properties make R the premier example of a real closed field. Proving this is the first half of one proof of the fundamental theorem of algebra. The rails carry a canonical measure, the Lebesgue measure, which is the Haar measure on their structure as a topological group normalized such that the unit interval 0, 1 has measure 1. There exist sets of real numbers that are not Lebesgue measurable, e.g., Vitali sets. The supremum axiom of the rails refers to subsets of the rails and is therefore a second-order logical statement. It is not possible to characterize the rails with first-order logic alone. The Lowenheim-Skolem theorem implies that there exists a countable dense subset of the real numbers satisfying exactly the same sentences in first-order logic as the real numbers themselves. The set of hyperreal numbers satisfies the same first-order sentences as R. Ordered fields that satisfy the same first-order sentences as R are called non-standard models of R. This is what makes non-standard analysis work. By proving a first-order statement in some non-standard model, we know that the same statement must also be true of R. The field R of real numbers is an extension field of the field Q of rational numbers, and R can therefore be seen as a vector space over Q. Zermelo-Fraenkel set theory with the axiom of choice guarantees the existence of a basis of this vector space. There exists a set B of real numbers such that every real number can be written uniquely as a finite linear combination of elements of this set, using rational coefficients only, and such that no element of B is a rational linear combination of the others. However, this existence theorem is purely theoretical, as such a base has never been explicitly described. The well-ordering theorem implies that the real numbers can be well-ordered if the axiom of choice is assumed. There exists a total order on R with the property that every non-empty subset of R has a least element in this ordering. Again, the existence of such a well-ordering is purely theoretical, as it has not been explicitly described. If V equals L is assumed in addition to the axioms of ZF, a well-ordering of the real numbers can be shown to be explicitly definable by a formula.